So yesterday I sketched how, with the idea of how with the classical Hodge theory, which I will again recall in some detail today, one can provide a mixed Hodge structure on the cohomology of a smooth variety. But in fact, Deline's Hodge 3 does a lot of homological algebra to say that all cohomologies associated with varieties can be built into. I mean, there's some more homological algebra where you have to put together double complexes and see that, cohomologies of double complexes acquire mixed Hodge structures and so on. So I don't want to spend too much time on that. Rather, I would like to say what is the connection with intersection theory. So in one place in today's lecture, I will refer to the mixed Hodge structures, but the rest of the time I'll be talking about pure Hodge structures today. Okay, so X if X is the smooth projective variety, then so what we have talked about yesterday is that you have an E1 PQ spectral sequence whose term is HQ X omega P X, and which converges to a hypercohomology of P plus Q, hypercohomology of the complex omega dot of X. Okay, so X is smooth projective variety, so there's no log and everything. It's all straight, somewhat easier. And the other thing is that we know from Grothendieck that this complex, there is a natural isomorphism of sheaf cohomologies to H and X omega dot of X. Yeah, and now the classical Hodge theory implies various things. So before talking about classical Hodge theory, I want to introduce one more element here, and that is an element eta in H2X Z, which is eta is the class, cohomology class of an ample divisor. So I'm just using A for ample, it's not. Okay. I suppose, yeah. So. Which one? Here. Yeah, so what? Ample divisor. Yeah, so I'll refer to the first Chern class later, but right now one can think in terms of cohomology classes of, okay, you're saying it may not be smooth. So then let's say some words. Okay, so as Srinivas says, one can think of first Chern class, but anyway, I will come to this. Right now I just, there exists a class, and the main thing is that in Hodge theory, I will write down certain statements which are the statements from classical Hodge theory. We'll talk about this. The basic point is that when I think of this as a cohomology class, it's going to be of, so we'll see. So first thing is that this spectral sequence E1 is equal to infinity. Right? So we mentioned this number of times. This is the degeneration of the spectral sequence, and this says that we have a filtration. So anyway, when you have a spectral sequence, you have filtration. So there is a filtration, and the filtration is given by Fk of H dot X omega dot X is image of H dot X sigma greater than or equal to K omega dot X to H dot X omega dot X, where by definition sigma greater than or equal to K omega dot X. So this is precise. Where sigma greater than or equal to K omega dot x consists of only the terms with, so this is omega xk, k plus 1 epsilon. And what this says is that the associated gradient Fp of h n of x omega dot x can be identified with h q, the E1 term. Right. And which we think of as HPQ for our Hodge structure, and it says also, by the way, so it also says that it is equal to the bar. I mean, that's also part of the Hodge theory. That's saying that the bar. No, I think it's correct. H. This is the numbering should be consistent. Yeah. H1O is H01 x, right? And which is a, I mean, in some sense, one should think of as it's a quotient of H. Right. Yeah. So it's a quotient of this by H1. This H1x by F1. H1. In fact, we'll see that tomorrow how that plays a role, but okay. I think not today. Okay. This is just an aside. Yeah. So that's the first thing. And in this terminology, this eta, so yeah. So of course, so far I have been talking only about working with cohomology with complex coefficients, but as I kind of started saying yesterday, we have to look at Z contained in Q, contained in R, contained in C, right? And so we can think of this as sitting inside H2x, Z sitting inside H2xC, and which I will identify with H2x omega dot x using this this isomorphism. And therefore I can talk about what is the Hodge type of this, and the Hodge type is of type 1,1. Okay. And so, as Srinivas said, one should, using the Dolbeau resolution, one should identify this with the harmonic PQ forms. I mean, that's part of the whole Hodge degeneration. And so, we should think of this eta as corresponding to a harmonic 1,1 form, and that's the Kähler class. Okay, so eta, so this should be somewhere. I mean, there's lots of machinery which one doesn't know which comes first, the Kähler class or all this. So anyway, so eta is 1 class representing the Kähler form. Okay. Except, yeah, so there is of course the usual 2 pi I business, so I will be cagey about that at this point. Okay. So that's the first thing, that you do have such a degeneration. But more than that is true. So you can take the cup product with eta to the power, okay, I think is this one. Sorry? That's right. So because it's an ample divisor, that's correct. Yeah. So the only thing which you have to worry about is factors of constant factors. So I will spend some time fixing the constant factors, whether it's that's what you would like. Yeah, it should be real because it's with real coefficients. So that's it. Yeah, but one has to be careful. When you look at books, you find that it's written as dz bar, and then the question is, how is it real? So you have to put an I there. Then. Okay, so where was I? Yeah, so this is what we have, and therefore this is a Hodge structure, And what is the relevance of this? Eta, suppose, so suppose B is equal to dimension X. And then I'm going to take the map B minus N plus 1, cup product with that, which is a map from H n of X C or even Z actually to H 2D minus 2D minus N plus 2 of X cup product. So cohomology cup product, and the kernel of this is defined as P n of X. Okay. So this is called the primitive part of Hn. And one can show that Hn is actually has tensor Q, it has a direct sum decomposition into P n minus X eta cup. Okay. So all this is part of Hodge theory, is to show that a certain collection of linear operators on the nth cohomology acts like the Lie algebra of little SL2, and eta operates as some kind of shifting operator, and so one can get this direct sum decomposition. Okay. What are the three operators? One is and of course it was not done originally. This is what was written down, and then yeah. But if you see Griffiths and Harris, then this SL2 point of view is given there. Okay. I mean so it's okay. It's SL2 point of view is not playing an important role for us, but the decomposition will play an important role, because the idea is that this decomposition, together with the fact that Pn xq cross Pn xq to with a suitable cup product, so x y goes to, so here I want H 2D x cube. So go to eta, let's see what I want, D minus N. Is a perfect pairing. Okay. So maybe this is, all this is part of the machine of classical Hodge theory. And okay. So the idea is that using this perfect pairing on each of these pieces and taking the direct sum decomposition, you can get a natural perfect pairing on Hn of X. Which will involve a suitable choice of signs. Absolutely. Which I am not even going to attempt in this on the board without, But there is a choice of signs. Okay. So the bottom line is that we get a perfect pairing Hn x cube. by putting together each of these pairings and using this decomposition. And as Nitin said, by correctly choosing the signs. So I will explain what signs you have to choose. That's one of the steps. Okay, is perfect pair with suitable choice of signs using the decomposition. And sorry, n is the nth cohomology, d is the dimension.
And so what are the indices? N, S, and
2d. Yeah. So it's not cup product to 2n. Okay, that is only on one piece, if at all, right? So you have essentially only on kind of what you might call P0, which is nothing but which is just one dimensional. So that's not very interesting, right? So it is something. It's more than taking cup product. You have to take cup product and then you have to follow it by multiplication by a suitable power of eta.
if n is less than, otherwise, definitely you need some.
Yeah. So right. Maybe no. Sorry.
N less than or equal to t.
N less than or equal to t. Okay. Is that necessary? Confused here. Yeah, otherwise, of course, this.
Well, you have written out one more part of the worksheet, right, which is that if n is less than or equal to t, less than d, h8 to hd qd minus n.
Okay, right. And then you can use that to pull it back. Okay, yeah, that's one more part of the machine. Thanks for reminding me. So there's the hard left shifts. I was going to mention that. So this is number 2. This is number 3. And then there's number 4, which is hard left shifts, which, by the way, has an interesting history because Lefschetz claimed to have proved it, but I think the first proof was using Hodge theory. So hard Lefschetz isomorphism. Eta to the power something. Yeah, sorry. The hard Lefschetz isomorphism, which is from d minus k x cube to h d plus k x. So this cup product is supposed to be an isomorphism, and Lefschetz claimed, I think, even that it was an isomorphism with integral coefficients, and he claimed to give a proof, and no one has been able to fix that proof as far as I know.
Therefore, not correct.
So, right. Well, at least then you would like to prove it's an inclusion with integer coefficients. I don't know even if that is true, but certainly the first proof which was accepted by the general mathematical public was using Hodge theory, and by proving it actually over complex numbers, and therefore, deducing that it is, since the map is, and since it is, sorry? Yeah, I think so. Essentially, yeah, I think so.
Hodge claimed lots of things also.
I see. So there is in this whole theory there is a kind of lineage, Poincaré followed by Lefschetz followed by Hodge, and I think it's only after that things became Kodaira somewhere, I suppose. Yeah. So.
Many people feel that his treatment will be good.
Yeah. Maybe. In any case, so. But in any case, this is a theorem. Okay. And so, as Nitin says, one has to worry about question of signs and so on, and a suitable, I didn't complete my sentence, suitable choice of signs. Okay. So hard Lefschetz gives an isomorphism, and then using that isomorphism one can get such a pairing on all the So this is called the polarization. So what I want to say is, first is that, you see, there's a lot of bookkeeping of the signs and the indices and so on, and the way I feel is that it becomes a mess unless one uses a slightly fancier terminal whatever system of keeping track of it, and which is a Tanakian formalism. Okay, so so I want to introduce that, and that will also reintroduce the explanation of the 2 pi I business which I talked about yesterday. Okay, so first step of that is to introduce this group. This is supposed to be blackboard bold S, which is the group x minus y, y x, x y, such that x square plus y square is invertible. So this group is nothing but, as you can see, that it's multiplication by, it's a matrix of multiplication by x plus iy, right? On the complex plane with the basis with respect to the standard basis 1 iota, right? So you will also see this written as RC over R of GM. Want a more direct explanation, this is what it is. Okay. So the claim is that real Hodge structure of weight n. Okay, before that I have to talk about weight, right? So of course there is a natural inclusion of GM in this, which is the diagonal matrices. And this is called the weight homomorphism. And so here is the basic one important step in the bookkeeping. Real Hodge structure of weight n is a representation, is the same as, so to speak, is, I'm sure Nitin will object, but I'll say it anyway, is a representation of this group S such that the GM operates by x to the power n, right? WGM operates by x to the power n. Okay, that makes sense. It's a multiplicative group. If I have a representation of the multiplicative group, then I can decompose my representation into direct sums of a single character, right? It's just how does x operate. So in this case, it's a pure Hodge structure. So now the terminology pure becomes clear, because you can make a kind of silly mixed thing, which Nitin was saying, not really mixed, which is just a direct sum decomposition depending on the irreducible representations of W. So what does this is mean? Is means that when I look at, we introduce the notion of Hodge structures with weights and so on, and let's take only Hodge structures which are mixed in a silly way, which is that they are direct sums of pure Hodge structures, and we introduce the notion of tensor products, duals, etc. And that category with its tensor products and the real structure and everything is in fact the category of the representations. And now of course there is still a question what is, but since everything is countable and so on, the equivalences are more or less canonical. Okay, so one doesn't have to worry too much about that aspect. Okay, so we want to think of real Hodge structures of weight n as in this fashion. Okay, and so what is HPQ? it's good to have an idea what is, so H, if H is such a representation, H, so maybe I write here, H, a representation of S of V10. Okay, then if I look at, so H is, of course, it's a real representation, right? It's a real algebraic group. I'm going to look at real representations. But I can complexify the representation. And as usual, and look at it as a complex vector space. And now once I'm looking at this as a complex representation, then it's going to decompose into, now it's again going to be a product of C and C star, right? And so you will get it in decompose into two parts, and you can just see, or you can directly see that this will decompose into H PQ, where this element, if I call this as Z, right, because it's this Z, Z operates as Z to the power P, Z bar to the power Q. Okay. So that's how the Hodge decomposition relates to the representations of S. Right. And now the question is, how is it going to help us do the bookkeeping? The idea is going to be that all operations in cohomology and all cohomology operations happen in the category of representations. Okay, so that's the philosophy, idea or philosophy. Okay, so you do everything in the language of representation theory rather than, well, it's not very deep representation theory, but keeping track of the representation or the action of S on this space is what will keep track of everything which you need to keep track of. That's the idea. Okay. So the first thing we want to do is to, if you look at it from the point of view of Hodge theory, everything else we have captured here except the notion of polarization. So the question is, what is polarization? Right. So on the one hand, what do I want? I want, for given a Hodge structure H, I want to have a pairing H cross H to, so for the moment, maybe even with integer coefficients, if you like, to Z, but of course then that is sitting inside HQ cross HQ to Q. Okay. So that's one other change which I'm making from the last 2 days to today. I will be talking about integer and at least rational coefficients. Okay, and therefore it's not just that when we talk about a morphism of Hodge structures, that is not captured here, so we'll come to that, but we would like things to be defined at the level of Q. And we know that for cohomology, the intersection and all those etas and all, everything was defined at the level of Q. Okay, so we'll talk about what, but as far as the definition is concerned, you could have done it at the level of R. Okay, but as Srinivas remarked the other day, since the irreducible Hodge structures in this sense for the representations of S are just one-dimensional complex vector spaces, giving a polarization is not very serious. But if you are thinking of an integer lattice, then defining a polarization means defining an inner product on an integer lattice, which should take values in integers, which is not entirely trivial. Okay, so there is something coming down here. But in any case, as far as for the moment, when we are thinking in terms of S, we'll just talk about what does it mean to have a polarization here. So I want a pairing. Okay, and what is the relation with S? Well, that's come at the end. Yeah, that will come at the end. Okay. You're building up to it. But then, of course, the groups will, well, Z, I don't know, Q, but it will get more and more complicated, right? Because the group will become bigger. So, the general philosophy, right? Again, if there are less things, then the group has to, because whatever you're asking for is going to be invariant under the group. So if there are less things which are invariant, the group has to be bigger to leave less things invariant. The smaller the group, the more things are possible. So with over real numbers, or there are lots of polarizations, but over integers there are going to be fewer polarizations. Okay, so what is a polarization? So polarization is such a pairing. And what is it that we require? So there is this special element here, which is I. Right. So it's called C for Cartan, or Weyl maybe. Right? Why is it called C if it's the Weyl element? The Cartan Weyl element maybe. Okay. I see. In his abelian varieties book. Variety scalarian. Okay. Okay. Yeah, so that's actually a good place where everything which I have is done, right? Variety scalarian. Yeah, but at least I think he would have taken care of lots of things. So I would imagine that he would be careful. Yeah. So maybe that's a good reference for. Well, first of all, language is French, so that too, maybe. Yeah. Okay. Okay. So what is the condition that we want? So you have a Hodge structure of weight n, and you have a pairing, and the claim is that, okay, there are two things. So first is that psi is invariant. So maybe I'll write it. Some terminology is required. Take elements in this of x square, the circle group, right? So you can kind of think of the circle group S1, which is sitting inside this, which consists of things where x square plus y square is 1. Right? So psi of theta, so to speak, I don't know. Let's call it E theta, x E theta y should be equal to psi of xy. It should be invariant under the circle. Okay, so that's one condition. And the second condition is that psi of x, and now I'm going to take note that C is E of I. So C of y is minus 1 to the power n, no, is, maybe I don't need the minus 1 here. Yeah, symmetric and positive. So the point I want to make is that if you use this convention, then that fixes the signs on each of those primitive parts that you would want to take. Okay, so earlier Nitin remarked that there's a question of signs for the primitive part. The primitive part, those inner products are pairings on each primitive part, but the sign was ambiguous, and this fixes the sign on each of those parts. Okay, in that particular case. So this is the condition, and just a remark that note that psi cx cy is equal to psi of xy. Right. On the other hand, what does symmetric mean? So let's call this phi of xy. Then phi of xy is equal to phi of yx, which is on the other hand psi of y comma c x. Right. So this is psi of, so I'm going to interchange the two and c y comma c square x, okay. I'm going to treat Cx as y or whatever in this equation. I mean, this identity I'm applying to some two vectors, and c square is minus 1. So this is going to act as minus 1 here, but note that minus 1 operates by x to the power n, so minus 1 operates as minus 1 to the power n. So this is minus 1 to the power n psi of yx. Okay, it's a very simple calculation, but it tells you that it has the right approach for the nth cohomology. We would like our pairing to be skew symmetric or symmetric depending on the parity of n. Okay, so this means that on weight n, the polarization has parity, has symmetry parity, as minus 1 to the power n symmetry. Okay, so this is what is in the sense of the representations of S, this is what is a polarization so far, is a polarization, is a pairing which satisfies these two identities, conditions. Okay, so polarization is a pairing, and because of the second one, it is definite. I mean, it is non-degenerate, right? Because this one is non-degenerate means the original one is non-degenerate, right? Because C is an automorphism. Okay. Any questions on this?
Yeah,
What does it mean? Well, I mean, you have a pairing, and we'll see. It plays. See, this positive definite is the part which is going to play an important role to say that what your category of mixed Hodge structures is semisimple. At least that's one of the consequences, right? You know that if I have representations, if I have something positive definite is preserved, then I can take orthogonal complements and so on, and therefore I can break up representations into irreducible pieces. So that's one of the things which we want to do. And the fact that there is something which is symmetric and positive definite will allow us to do that. Okay. I mean, so there are other consequences, but anyway, by the way, so this in some sense, though I've written this after the Hodge theory, classical Hodge theory part, this part is also proved in the classical Hodge theory, that you can choose the sign so that you can make it positive definite. Okay.
So this also induces a polarization on HC, and you are saying that on the HPQ part, minus 1 to the power p psi is positive definite. That's what you're saying.
No, right now it is not a polarization on HC. I mean, it is a pairing on HC. But, so what's your question?
I'm saying that this induces minus 1 to the power p on HP is the positive definite inner product.
Okay, let's see what it means on HPQ. I'll just do that. Thanks for reminding me. But I have not said it in terms of HPQ so far. I'm only talking about HR. Okay, so it's positive definite in the sense of a real.
What do you mean by on a weight plane it is minus 1 to the power n? HR is a single vector space, right? You have not given a decomposition of HR.
Yeah. So what?
So what do you mean by on weight n?
No, weight n. No, HR is of weight n. So, since HR is of weight n, maybe I should have said. See, what does it mean to say something is of weight n? That means a real number x operates as x to the power n. So, minus 1 operates as minus 1 to the power n. C square is minus 1. Okay, so it operates as minus 1 to the power n. So far I have not talked about what happens over complex numbers, but let's see what happens. So if you take a complex number, right, and of absolute value 1, we already said, so what is the consequence of this part is that you can again use the symmetry, right? So E theta x, E theta y, and get out the scalar, so is equal to xy, right? So what I want to say is, so why am I getting stuck? I want to claim, let me write the claim first before I confuse everybody, is that Fp perpendicular with respect to psi is F n minus p. Or if you want, another way to say it is that HPQ is going to be paired with HQP. So are paired under psi. Okay. I think. Mm-hmm.
That's like the J operator,
Which one? Yeah, this is a complex. Well,
HR itself gets a complex.
not on the middle one, no. On the PP part, it will operate as -1 to the power p or something, I mean, whatever, right? I mean, yeah. So it's not a complex structure as such.
For a certain weight.
For the p not equal to q, that's what we said yesterday or day before yesterday. Okay, for p equal to q, you don't get anything.
That complex with the space is coming out of this one, J operator, right?
Yeah, if you like. So the weight, that's what I was trying to.
Round bracket PQ
Right.
is getting its complex structure. Not from C.
Yeah, so one has to be a little careful because there's a power. There's a
Raising the sum power combined with the power.
right. So it's z to the power p, z bar to the power q. So I is operating as I to the power p minus q, not I. Okay. So C. So how is C operating? Yeah. So let's see. Yeah. Now I remembered what I do. So suppose I take H in HPQ. And Y in HRS, right? I mean, I can, of course, I have a pairing. I can extend it by complex numbers. So I'll get a pairing. And then what is E theta operating as? E theta is operating, let me say that I will get thoroughly confused. So if I try to get the notation, so I want to say E to the I theta or T, let me call it T. T to the power p, t to the power minus q, right? If you have a complex number of absolute value 1, its bar is its inverse. So on this part it operates as t to the power p, t to the power minus q. On that side it operates as t to the power r times t to the power s, right? So what's coming out is p plus r minus q minus s, right? And so you can see that, so that's going to be a problem, right? On how can it be equal? So you'll get t to the power p minus q plus r minus s psi xy. Now, so assuming that p is different, if p and q and r and s, okay, something will happen, but p minus s is, so yeah, also we know that p plus q is equal to r plus s, right? So I can take p minus s, which is, call it m, this is equal to r minus q or something, right? If this, my multiplication is correct, this means that p minus s is equal to m, which is equal to r minus q. So this will be t to the power 2m psi xy. Okay. So now you can see that if m is non-zero, you have a problem, right? This is true for all t of absolute value 1. And how can you have equality of these two numbers if m is not 0, right? So that proves that this and this are paired under this pairing. Okay. In other words, the pairing in some sense is taking the, so this was your question, HPQ is paired with HQP under this pairing.
What you mean is HPQ is orthogonal to everything else?
Except, right, thanks. Yeah, so it kind of, the orthogonal decomposition, well, I don't know, that's not the right word. But the decomposition has something to do with the pairing. And what it has to do is that the HPQ is getting exactly paired only with HQP and nothing else. All the other dot products are 0. Okay. So there are a lot of attempts to do Hodge theory where the bookkeeping is done without using this group. In a lot of places where they want to be very elementary. So for example, Wikipedia. So if you see Wikipedia, there's no mention of the group S, but instead it is said that a polarization is something which has this property and this positive definiteness. Okay, so it's said entirely in terms of linear algebra, but I think that's somehow misleading. It's elementary by hiding something which is, of course, Nitin, I'm trying to do that here also, but anyway, okay. Okay, so I hope the idea is clear that this has a lot of implications about the Hodge structure. It's not just a pairing, it has this additional property that it has this perpendicularity condition. But we would like to have more. As I said, we want to get it, we want to understand what happens at the level of integers also. Okay. And this is where the thing that I talked about yesterday will play a role.
And also, in a sense, you cheated, right? Because HR was a representation of some groups.
Right.
But this polarization only uses the representation of the subgroup S1.
Yeah. Yeah,
right?
very good. What is going to happen, right? So ideally what you would like is your bookkeeping should take care, as Srinivas says, of the fact that this is in some sense a pairing in that category. That means you should have the representations on all sides. That means so you should identify what is the correct representation on this side. Okay, in order to get such a pairing. And if you think about it, the pairing, if it is supposed to preserve all the actions, then this is of weight n, this is of weight n, so this should be of weight 2n, right? So how does the question which comes immediately to mind is how do I think of this as weight 2n? Well, we've kind of answered it when we talked about Hodge structures, because a one-dimensional Hodge structure of weight 2n, there is exactly one, right? So ideally this should be r minus n, what we call r minus n, okay? And I want to justify today, the next few minutes, why there's a minus here. So you've got a pairing, but ideally it should be in r minus n.
What's the action of C?
Action of?
C, that operator.
I to the power whatever, right? Minus 1, so I to the power n into I to the power n bar, which is 1. So, I mean, it's a type n, so it should be operating by I to the power n. No, I don't think. I think the C operation is trivial because this is, yeah, I mean, in some sense, that's what you were saying, that the theta part operates trivially, right? I mean, so the S1 part operates trivially. You really have to see somehow out of the real number part, out of the scalars, the weight should somehow come there. The action of GM of R, the diagonal matrices has to be understood. Okay, but that is tricky because as such, well, it's not. That's how you would say it, because if you take a cohomology class and you multiply two cohomology classes by a constant, you expect the pairing to multiply by the product of those constants. And so if you think in terms of integers, n times a class, m times a class should give me nm times the pairing. And so that should come out. But then that is just the product of these two integers, but how does that translate into the action of the weight? So one has to see. Okay. Sorry?
We began with the group C star.
Right.
Consider the real group.
Right.
Its implications.
Mm-hmm.
And there was no reference to any
Nothing.
So where did the indexing go from 0 to something positive? Where does this positive come from?
No, nowhere. I mean, it can be negative also.
Right.
No. There's nothing here which says that n is positive. No. And there's nothing which says, I mean, I think somebody asked, maybe you asked this question earlier, that we are not concerned about whether P and Q are positive or negative at this stage. They could be negative. All we know, they are only finitely many.
But the diamond shape does it.
That's for a smooth projective variety, yeah.
And for cohomology.
And for cohomology, you can do homology.
Using some duality to make it.
Then you will get negative weights. Anyway, we're jumping the gun, right? So let me quickly sketch what I was saying yesterday about how to get the class. So what I want to do now is I want to understand very specific cohomology, right? And ideally, somehow computing this should tell us everything, okay? And this is called the Tate-Hodge structure, or maybe it's the Tate inverse or Lefschetz-Hodge structure. I always get confused anyway. Okay, we'll see. So we want to understand this, and we understand it, as I said yesterday, via the short exact sequence, the exponential sequence. So which is of course for a general x. Where this map is f goes to exponential of f, right? And as was remarked yesterday, you have a commutative diagram. Where this is your exponential map, right? This is D. And this map is G goes to dg by G. Okay. And f goes to exponential of f. And that's the usual calculation. D of exponential of f by exponential of f will be D of f. Right. Calculus. Okay. So this complex maps to this, and if I throw away, since these are equal, I will throw it away, then I get on the one hand, this diagram says that I have a map from h1x ox star to h2x, and I want to keep track of this, 2 pi I z, okay? But that map is compatible with the map from this to h2x omega dot x, okay? And where the h1x ox part goes to 0, so in some sense I'm identifying the image of this with the image here, okay? And that image here is also, if I'm forgetting about this part, is actually landing inside f1 of this, okay? So that is a way to justify that this should be thought of as 2 pi I inverse of z, right? Because this one has a natural element, so this I should think of as z, as the trivial Hodge structure. So if I want to think of H2 P1 with values in 2 pi I z as the trivial Hodge structure, because there's a natural generator there and everything is a multiple of it, then that means that this should be identified as 2 pi I inverse z. And 2 pi I inverse z, and what is when I say trivial Hodge structure, this means that it should be of type 0, 0. This should be of type 1, 1. Of course, we know this should be of type 1, 1. So that means 2 pi I inverse z should be of type 1, 1. So it is a Hodge structure of which should be r minus 1 when I do it correctly. So remember, r minus 1 was only picked up to a choice of basis. So now it has told me that the basis is some multiple of 2 pi I, okay? So it doesn't matter in some sense, but the I is important there. If you work with Q coefficients, the pi is also important. If you work with integer coefficients, the 2 is also important, right? So, which now therefore I will think of as, and that's the reason why this notation minus 1, because 2 pi I to the minus 1, so it's supposed to keep track of the 2 pi I minus 1, but it is of weight 2, okay? So it's z minus 1 is of weight 2 and is type 1, 1. Okay. So I hope the reasoning there is at least it's a kind of justification, and Dalin has written some further notes because he's also interested in knowing what is the sign of the class, whether it's with a plus sign, minus sign, and things like that. And that depends on, as Abhyankar says, you have to know which is I and which is minus I, and so on. So you have to fix a choice of I that fixes a choice of orientation, and then you have to see whether so the four possibilities are talked about in Dalin's paper and her theory. But at this stage, we are not going to worry about it too much. Okay, there's some further bookkeeping which is required actually to keep track of the sign.
Just to flag one of the homological algebra tissue, you wrote a mark from H1 OH star to H2 microchrome.
Right.
So really I'm thinking of the OH star as a complex living only in degree 1.
Degree 1, yeah.
And taking
Yeah, so if you want to do it, you're right. If you want to do it correctly, you should think of this as an H2 and that also as an H2.
Exactly.
And then you have to do the sign correctly.
Two things. One is a shift operation, and then depending on the information, shift operation will produce some sign.
Yeah. So though it is, we'll see an example of this later when we are doing GISIN and so on. I hope. So, okay. So I'm going a little slowly perhaps. Okay, so where were we? So now what I want to say is, therefore, I should think of the polarization, if I want to do with integer coefficients, to taking values in z minus n, right, when h is of weight n. And just a quick warning, I'm not saying this is a perfect pairing. Tensor Q, it's a perfect pairing, right? I mean, you don't expect cup product to be a perfect pairing on integers. Okay, so what about torsion? So you do have, I mean, that is one problem, and also you may get perfect in the sense that everything has something to which its dot product is not zero, but that's not the same as saying that the dual is there, because we have chosen some ample class.
I think when you do like this, but I'm saying there are things where it is perfect over there.
Very good. Yes, of course. Yeah, I mean, yeah. Okay.
No, so that's a strong restriction somehow on the
Right.
what you
Yeah.
get.
Mhm. Yeah. So the other thing which is worth seeing is that if you look at your ample class, right, then its dth power, d is your dimension, gives you an element here, and so that should be identified as z to the, this is the generator here, so this should be identified as z minus d, okay, which is correct for x equal to p1 and d equal to 1. Okay, so that explains this convention where d equal to dimension, right? If I know that the dth power of the ample class generates this cohomology. So what this tells me is that you can now say tensor product in the sense of some representation theory and say that a pairing is a bilinear map of Hodge structures with this notation. And of course those conventions about positive definiteness has to be put in separately. Okay, so the objection or whatever the remark which Srinivas had about asking for invariance under only the circle group has now gone away. Okay, now everything is happening with the action of the S itself. So this is a morphism of representations of S, but with one more condition when it's a polarization, that twisted form psi, so maybe I should write it here. H is of weight n, a polarization is a morphism of Hodge structures such that psi x cy is positive definite. So that condition we can't drop. That is something which is.
So when the working over Z and talking about representations,
Mm-hmm.
they are the working over Z defined by that.
No. I mean, when we will go to R to talk about the representation theory. But the tensor product and everything makes sense over integers. So it's a category with tensor products. And the morphism in the sense of representations is, so if you want to say it correctly, so I have a functor. Right? And whatever morphism I have, it should be a morphism of representations when I go to the image here. Right? So this is tensor R is this functor. Okay.
You have not brought the group to this.
No, we have not brought the group to this side yet. Okay. I don't know if I'll be able to do it today. Which one?
What you defined S.
But no, that yeah, but that's the wrong group. I mean,
That's too small.
that is, well, also it's too simple. It's an abelian group. I mean, you don't expect to have only abelian groups. Okay, so since Nitin pointed out, it was correct to say that when you're looking at integer or rational Hodge structures, that is a category which has tensor products and all. We can just define as before. I mean, we know how to take tensor products abelian groups. So yeah, I should have said that somewhere, that this is always going to be finitely generated abelian group. Okay, so if we are working with vector spaces and so on, we don't have to say automatically if the, not necessarily. So okay. As Srinivas says, maybe most of the things should be done with Q coefficients. But there's some interest in the integer coefficients. I mean, so that's why I'm keeping track of it. Okay, so you have a underlying finitely generated abelian group and with a Hodge structure, which means that I actually have a functor here, okay, and I'm looking at the object there, right? So I want to say that means it's nothing but HR has a Hodge structure, right? And I have such a pairing which is defined at the integer level, but at the R level, it's a morphism of Hodge structures, real Hodge structures. And at the R level, of course, positively definite and all that is at the R level, because C is operating only at the R level.
This functor is not faithful.
This functor is not faithful because, of course, if there's something which is purely torsion, tensoring it with, it will become 0. Sorry? Is tensor R, right? Means nothing but a finitely generated abelian group and with such that this carries a representation of HR. Okay, so if you want to some tuple kind of thing, HZ and a row which is going from S to GL of HR. Okay, and if you want to put weight n, then such that W is x to the power m, right, where W is that subgroup of scalars. Yeah? Hybrid. Okay. Yeah, it's a patching. Okay. So we have so what this allows us to do more, if we have formulated it like this, well, if you want to formulate with Q coefficients, of course, there's still Nitin's question, what is it to be defined everything, at least for Q, directly on this side. But for the moment, let's grant that that's not a very serious wiggle. We would like whatever we do with cohomology of algebraic varieties to be done with values in this category rather than the category of finitely generated abelian groups. Okay, so that's the idea, that we'll get everything as a, so for example, if you have a morphism of smooth projective varieties, Then, of course, if I just do Hn of this, it goes from Hn of y to Hn of x, no problem. As you can expect, it will be a morphism of hot structures. Okay, that is not the serious one. The serious one, because we are working with so if you are working with homology, it would be the other one which is serious. But the intersection theory is going to come in trying to define the map in the other direction. Okay. So what is the question is, or how do we understand the map Hn of x to a suitable Hn prime of y, right? The push forward. They are projective varieties, smooth projective varieties. Okay, and this is where it will mirror intersection theory. As I mentioned, the indices look a little different from intersection theory, but that's because here we are working with cohomology rather than homology. Okay, and that dualizes everything. So it's a mess which unfortunately exists in the theory that everything in cycles is normally done in the homology sense, but here it is, everything is cohomology. So how would you do it at the level of cycles? So how do you do this push forward map at the level of cycles? Well, push forward, push back, well, pull back in the case of cycles, right? So if you are thinking in terms of cycles, you would be writing the dual map. So one way is, if you are working with Q coefficients, you can use Poincare duality. Everything is smooth projective. You could have just done everything with Poincare duality. So Hn x is paired with h2d minus n x goes to h2d x, right? Q coefficients now. And yeah, and so you would get h n x is isomorphic to, this is a perfect pairing, so this is h n star, and now you would take h 2d minus n x f, so to speak, star, right, which would go to h 2d minus n y star, and then you would go back to h 2d prime minus 2d minus n plus n y. Right. So this is one approach using Poincare duality. You would get a map in the opposite direction, and which does, as we expect, does have a shift of dimension. So you get a map from Hn x to, or strictly speaking, whatever. Okay, you know what I mean. So you could think of it as Hn minus 2d n plus 2d x to Hn plus 2d prime. But one problem is that we haven't kept track of the twists, okay? But that we can do. Here we know this is z minus d, right? And so you would have to put a twist of d minus d here. Okay, so that, and you don't actually need to do you don't have to keep track of it there, because we know that this should be a morphism of hot structures. If it's a morphism of hot structures, they better have the same weight, right? And so this has weight n plus 2d. No, so I've done it wrong clearly. Should have had minus d. Okay, so now it's correct. Okay. So I want to weight here to be n, weight here to be n. So you expect to get a map. So if you just use a Poincare duality, then you expect to see a.
Could you explain that notation again? What is bracket B?
That's a twist tensor with ZD. So maybe I'll write it here. So what I want is, I want to think of a map from H2dx z bracket d, sorry, n plus 2d to h n plus 2d prime y z bracket d prime, where d is dimension x and d prime is dimension y. Okay. Is there a question? This twist makes a shift minus 2d weight. So this becomes a weight n. This is also weight n. And we want a morphism of hot structures of weight n. So that's the correct number, right? So you can see the utility of the bookkeeping is very immediate once you do it correctly. I mean, you don't have to do it in the intermediate steps at the end. You can keep track of it. Of course, if you want to keep track of signs, then you have to probably be a little more careful. Okay, but of course, I have actually written it down with z coefficients, but the map way I've defined it, I've done tensor q coefficients. So you would like to do it actually with integer coefficients if possible. And how will you do that? So that's where whatever we have learned in intersection theory becomes useful, right? How do I try to do the push forward? Sorry? Why is it a map of hot structures? This is a map of hot structures. Well, okay, so you're pulling me apart. Okay, so one has to be a little careful. You're right. So you would have to put appropriate twists in order to make it a map of hot structures. Okay, and that's where all this keeping track. So the way it is done in Griffiths is that he doesn't keep track of the weight of the hot structure. He only keeps track of the circle action. Okay, and that part one can check it's compatible. And right, and then you have to see that the weight is working correctly. So it's a little bit of a mess. So I'm giving, this is supposed to be the heuristic. I want to give you an explanation which does not have all this. No. Correctly speaking, it's a map of hot structures because of what I'm going to say now, which is that how do you do intersection? You take external product and then external product, and then you intersect with the diagonal. And so one has to understand how to do intersection with the diagonal, right? That's the only way. I mean, and we have to understand how that works at the level of Hodge theory. Okay, so I don't know how it is done classically. Today I'm going to cheat, and I'm going to use the idea that even though we are working with pure Hodge structures, because everything is the functor is of cohomology is defined at the level of mixed Hodge structures. In the middle, I could use a mixed Hodge structure as long as I know that it is pure. I mean, I know there's a morphism of mixed Hodge structures, and because the functor x. Anyway, you'll see what I'm going to do. Yeah. Right.
What do you know what covariant duality does to
Same question, right? Exactly. Yeah, you have to work with it. Yeah. So it's not so straightforward. So that's why I drew this. I didn't realize that I didn't explain. I wrote this as motivation. It's not a proof. Okay. Now I'm going to try to make it into something more rigorous. Okay. Not necessarily a proof in the stronger sense, but at least from the point of intersection theory, it would be easier. So you take your usual way of seeing x as a graph inside x cross y, right? And then you like to do integration along the fibers to get to y. So this is the usual way in which you would like to get a map like this. You would like to push it first here. Here there's nothing. This is an isomorphism. But from here somehow I have to push it into this. And then from here to here is also not too difficult, because integration along the fiber means what? Means I should just take the piece corresponding to the top dimension in x. Okay, so that's the Kunet piece, and actually there's a Kunet filtration, so you don't even have to worry about integer coefficients, or you can write some Kunet spectral sequence or something. But in any case, you do have a map H n of x cross y with integer coefficients to H 2d of x z tensor h n minus 2d x y z. Okay, so this one can show that this kind of a map is actually at the level of Hall structures. That is part of what is called the Kuhn spectral sequence, or in this case, if you don't want to do with integer coefficients, it's the Kuhn decomposition, right? And the Kuhn decomposition actually comes from writing some kind of a relative version of the mixed Hodge theory. Okay, so that's why I said that there's some mixed Hodge theory built in somewhere inside this construction, if you want to do it correctly, right? Okay, so there is such a map of Hodge structures, and this is ZD, Z minus D. Okay, so that's where your Z minus D factor is coming. So you're going to shift it here, and you're going to get a ZD here. Okay, so this part is relatively straightforward. This is the integration along fibers. So the remaining thing is, what do you do to go from Hn of x to Hn of, which is isomorphic to Hn of gamma f, and how do I go to H, whatever suitable number of x cross y? And we know what we have to do from intersection theory or Gisin and so on, is that we want to think of cohomology, some m, let me just call it m. And then we'll identify M with supports in gamma f of x cross y, right? But we know that in this context we can replace x cross y by the normal cone. So the way to go here is to take here Hm of gamma f, normal f, gamma f in x cross y. Okay, because everything is happening along x gamma f. Now, this would be a mixed Hodge structure, but this we know is, this cohomology is actually just the cohomology of f with some, via the Gisin homomorphism. And so all it means is that we have to see what happens in the Gisin homomorphism, which amounts to multiplying by suitable top Chern class of the normal bundle. And that we know what the twist is, because we know what it is for the first Chern class, and top Chern class is just iteration of this. So the nth Chern class is going to have n, it will be of type z minus n, right? So therefore this one will be gamma f with whatever is the normal, which actually happens to be y. So that's where the d factor comes in. So maybe I won't go into that. It's just straightforward, right? So I hope the idea is clear that this is equality with some suitable numbers here and with the twist thrown in here. Okay, and therefore you get a map to this, and then using the map from here to here and to this, you will get the push forward. Okay, so and and we know how to keep track of the numbers, because we know how to, and everything will be a map of Hodge structures. So the advantage of doing it via this is providing that we have shown that there are mixed Hodge structures on everything, and all the morphisms associated with varieties are morphisms of mixed Hodge structures. This will be a morphism of mixed Hodge structures. Okay, and so will this map be a morphism of mixed Hodge structures. So, but they are all pure, and morphisms of pure Hodge structures considered as mixed Hodge structures are pure morphisms of pure Hodge structures.
The first one, the normal core one is the one which argued directly with geometry is pure. The other one I'm talking something mixed.
This is mixed.
And it's isomorphic as it's a map of mixed Hodge structures, which is an isomorphism of abelian groups. Therefore, the other one is pure. Therefore,
it's pure. Right. Thanks. Yeah. So that was the remark, that this is an isomorphism, is because we know that it's an isomorphism at the level of cohomology. Okay. So the ideas of intersection theory certainly play a role, and you can extend this and to talk about something which will be talked about perhaps in terms of cycles, is that in terms of correspondences also we will get given a correspondence from x to y, which means a cycle on x cross y. By doing the same kind of reasoning, we can go from x to y with some appropriate shifts. We will get morphism of Hodge structures. So what is it that we would like to achieve? So let's work with even Q coefficients for the moment. So there is a category known as category of Q pure Hodge structures of which is where now I'm not going to, they're direct sums of pure Hodge structures. So maybe you should call it quasi-pure or whatever. I mean, unmixed Hodge structures. Okay, so take QHS to be the category of unmixed Hodge structures. And now we have produced from varieties over C a kind of functor in which all the cohomology theories go on this side, right? So every morphism of varieties gives rise to corresponding morphisms of Hodge structures in both directions. A correspondence here gives rise to a correspondence and so on. The question we should ask ourselves, are we hitting everything? Okay, so this you can say is the generalized Hodge conjecture, is to say that everything which happens on this side, does it actually come from varieties? Okay, so the answer is unfortunately, or maybe interestingly, no. Okay, so the first problem which is identified by Griffiths and which is explained in Deline's Travaux de Griffiths is that there are Hodge structures which don't come from varieties at all. So there are things here, okay, which have nothing to do with varieties. So there are Q Hodge structures which, in some sense, some kind of countability, uncountability argument one can do, okay, to show that there are Hodge structures which don't come from varieties. Now, therefore, you now restrict your attention to varieties, those Hodge structures which come from varieties. So take the target in the sense of objects at least are of the variety kind. Now you can still ask the question, are morphisms coming from varieties? Okay, and that is the way in which you can say the generalized Hodge conjecture can be stated. So the generalized Hodge conjecture says, if you want to phrase it in this language, is the statement that given two Hodge structures here which come from varieties, is it come from varieties? Or which is actually, it's a weak way of saying it. Note that there is still one small question inside that. If you take a Hodge structure and you write it as a sum of two Hodge structures, if the original one came from varieties, how do I know that the two sub-Hodge structures come from varieties? So that is what you might call as the Grothendieck's generalized Hodge conjecture. So I think it's not quite stated that way in Hodge's paper, but there are two questions here. So this is a no at object level. Okay, but hope yes at morphism level. But there's an object level question which is still there, which is that if an object which is in the image, which is the cohomology of an algebraic variety, and if I write it as a sum of two things, is at least one of the things coming from varieties. Okay, and then the other one will by projection or whatever.
So this functor is faithful is part of it.
Faithful, I'm not, at this stage we are not talking about the kernel. No, I mean rational equivalence will go to zero, right? So two morphisms which are...
Yeah, but then you know the kernel.
That's a separate conjecture which I'm not getting into today. Okay, that's a separate issue. Is it one-to-one? Here we are talking about on-to.
And the direct sum on the other side is
Mm-hmm.
going to correspond to some kind of operation in the one.
Correct.
And if this is...
So you can state it, you can try to state it that way also. Yeah, you can try to state it in that way also. That a projection will be a... Yeah. So the usual way in which it is stated is that if... anyway. So there is a part of the Hodge conjecture which is to say that if at the object level, if an object exists, then its direct summands are coming from X, okay, and morphisms are coming from X.
Okay. That will be the case in the usual Hodge conjecture and X dot.
Correct. Yeah. So I'm a bit confused. It's all conjectural. I'm trying to think. maybe the point is, okay, maybe generalized Hodge conjecture is saying that if you have a Hodge structure of positive weight n, then it's coming from a variety of dimension n.
If you have a sub-Hodge structure of your given Hodge structure, which is a smaller width, then it comes from a
Sub-variety of smaller dimension of a co-dimension. That's the usual statement. I was trying to get it in terms of surjectivity. Maybe I'll have to think about it. Maybe you're right. It's not that straightforward. Right.
So this function feels more than rational equivalence?
Definitely. Algebraic equivalence. So algebraic equivalence is homotopy, therefore it's going to go to 0.
So there is no better history for this?
So that we'll discuss. Once you go to mixed Hodge structures, you can hope for better. Even for pure varieties, one can hope for better if you go to mixed Hodge structures. Okay, so. Yes. So I should have said, when I'm writing here QHS, I mean polarizable. Okay. Otherwise it's more or less obvious that without the polarizable condition, there's no chance. So that is already a restriction which is required. I mean, somewhere I should have remarked that the reason for introducing polarization is to cut down the target, right? Otherwise, you are looking at too big a category of vector spaces. This is not a reasonable to explain.
You have some kind of semi-simplicity.
Semi-simplicity, lots of things. Yeah. Right. To say the classical statement of the Hodge conjecture is the assertion that if you have a class here which is of type PP, integral class of type PP, then it comes from a cycle class, and that is under this push forward. It means that it comes from H. So class there means Z sitting to homomorphism from Z to H to N X Zn of Hodge structures. Okay, so that's one way to look at it. Well, that's because it was found that the Hodge conjecture, quote unquote, is false for trivial reasons, because without the multiplication it's false.
No. The general Hodge conjecture was false for other trivial.
That is the other one. But even this, IISER gave an example, right? So I don't know what Hodge exactly conjectured. In fact, it's not even clear that Hodge made a conjecture. He stated a problem. Okay, everyone jumped on it and said conjecture. But I should, I mean, some of the things one can't talk about. I mean, there's too little time. But for n equal to 1, it's a theorem, right? And that's the Lefschetz 1-1 theorem, and it is true with integer coefficients. So therefore, Hodge may have thought that it is true for other n with integer coefficients, but it turns out to be false with integer coefficients. And that is the IISER example. And then later on, there are other examples of Kolar and so on. So there are many examples to say that you can only expect this to come from a cycle class in the sense of push forward after tensor Q. Okay.
Which is instead of ordinary cycle, we work with so-called étale cycle. Then you expect it to work efficiently. That's equal to this theorem.
I see. Okay.
There is an integral statement.
Oh, there's an integral statement which is equivalent to this. I see. Okay, that's nice.
This version is not correct.
This correct.
That is so-called étale.
I see. Interesting. Okay. I didn't know this. No, I mean, you may have taught it, but you may not have clarified this point at that stage while giving the talk. I understand, but it may have not registered adequately. Okay.